Cool. All right. Good day, everyone. Here is your second lesson for the week 6 lockdown, which is about processing the rules to help you determine oxidation number. Really important lesson for two reasons. First reason is because all of the equations I've given you so far have shown you where the electrons are. But in reality, we're not going to put the electrons down for you. You will need to figure out which side the electrons go on. And so in order to help you figure out which is the oxidation half and which is the reduction half, you're going to need to use oxidation numbers. The other thing is you're going to be using these oxidation numbers to help you justify how you know something's oxidation and reduction. So I just want to introduce you to this so you can learn the process of how to figure out the oxidation numbers. Next week, I'll show you how to use them in equations. So let's look at that for today. You are doing number 3 on your checklist, just figuring out the rules to determine oxidation number and also how to use multiple rules together in the concept of oxidation math to figure out what the oxidation number is. So the thing I have to also add is that with these rules, we will not give these rules to you on the assessment, so you do have to have them memorized. But they're pretty easy and logical, I would say. All right, so let's start and talk about what oxidation numbers are. So oxidation numbers are assigned to elements in a chemical reaction, and we check these oxidation numbers and we see if there's any change from the reactant to the product side. This then helps us determine if something is an oxidant or a reductant based on how that number changes. If the number does not change, it tells us it's not part of the redox reaction. So if the oxidation number increases, that correlates to a loss of electrons, and that is an oxidation reaction. So from reactant side to product side, if I see that number go up, then that is an oxidation, or that's the oxidation half, because that number can only go up if we lose electrons. Remember, electrons are negatively charged, so losing it makes my numbers go up. If the oxidation number decreases from the reactant to the product side, I have gained electrons, and thus my reduction reaction. Again, remember, electrons are negatively charged, so if they're added to the element, the oxidation number will decrease. So here are the list of rules. I'm just going to go through them, and then I'm going to show you guys some examples so you can see how to apply it. And like I said, you will need to memorize these rules. We will not give them to you, but I think they're pretty logical. So the first rule is that the oxidation number of anything that's in the elemental form, so it's free, it's uncombined, it's not a compound, it has the oxidation number of 0. So this is going to be really obvious in things like aluminum and zinc or other metals, but this is also true for diatomic molecules, triatomic molecules, so long as the molecule has all of the same elements, so a 2-atom or 3-atom element. The example I have for you would be hydrogen gas, H2. That is a diatomic molecule. It is still an element, so its oxidation number is 0. The second rule then is when we're dealing with monoatomic ions. So basically ions that only have one atom involved, and whatever the charge of that ion is, that is the oxidation number that that element has. Rule number 3, and this is stuff that we're now going to start combining to kind of help us do some oxidation math. Rule number 3 states that if I have a neutral compound, and I know compound's neutral if there's no charge on the end of it, the sum of all the oxidation numbers is 0. So when I add all the oxidation numbers of the different elements together, they should add to 0. It just helps me set up basically for an algebraic equation. Rule number 4 is very similar to rule number 3. The only difference is that instead of being equal to 0, it's going to be equal to the charge of the polyatomic ion. So the charge of the polyatomic ion is equal to the total sum of all the oxidation numbers in that polyatomic ion. And again, I'll show you some examples of it. Rule 3 and 4 are very important when we do stuff that I like to call oxidation math. Cool. Then there's a list of things that are some things that are very specific to certain elements, and even if they are specific to certain elements, there's also exceptions to that. So the first rule is that oxygen in a compound is usually -2. So remember, if I have oxygen as the element, O2, the molecule, it follows rule number 1, and its oxidation number is 0. So I'm talking about oxygen in compounds such as in water, H2O, and the oxidation number of the oxygen in that water is going to be -2. There is an exception, and that is if the oxygen is in any peroxides, for example, hydrogen peroxide. In this case, the oxidation number of oxygen is -1 instead of -2. So do keep in mind that that is an exception. Another exception is if my oxygen is bonded to fluorine, and in this case, the oxidation number is instead +1. Really important that you remember these exceptions, but generally when you're dealing with oxygen, you're going to be dealing with -2, and I should say if it's in a compound. So keep in mind all these little kind of like asterisks, and like I said, I'll show you how to apply the rules in a moment. Rule number 6 is for hydrogen. So hydrogen in a compound, and again, compound is the key word, is +1. Like I said, if I have H2, the element, the molecule, it is 0, following rule number 1. The hydrogen part, so hydrogen in a compound is +1. Again, it does have an exception, and that's in a metal hydride. So basically a hydrogen with a metal. And in this case, the number for hydrogen is going to be -1. Again, you'll see this when you come up in your homework and various practice, that there are applications of these exceptions to the rule. All right. The last one is about oxidation numbers of the halogens. So fluoride is always -1. Same with chloride, bromide, and iodide. Normally has an oxidation number of -1, unless they're combined with oxygen or fluorine, and that can then influence its number. We will use oxidation math then to figure out what its number is. So those are the rules that you guys need to memorize. I will show you some applications so you can see me apply the different rules based on what I've been given. So I figured the best way for me to show this to you guys is look at the oxidation number of chromium. Now, obviously, I have a whole list of chromium in different situations, and that's going to influence what rule I grab and thus what oxidation number I have. So once again, I'm going to move to my OneNote so I can write these notes down. I wonder if there's a way I can like zoom out so you guys can see it. There you go. All right, maybe zoom in a little bit more. Alrighty, and let me switch over so I can draw on my computer now. All right. So what I'm going to do is I'm going to write, and I'm going to go through each one and kind of flick back and forth from the rules to the example problems. So I'm looking for chromium. That's the only oxidation number that I'm looking for in all of these examples. So the first one here is chromium. Now I can see that chromium is in the element form. I know it's in the element form because it's chromium by itself, and I can see there's no charge there. So that means that the oxidation number in this example, and you can abbreviate that as ON, is going to be 0 because rule number 1, the oxidation number of the element in its free form is going to be 0. And I like to do that little cross throughs, that way we can tell the difference between O's and zeros. I'm going to switch colors so that way we have a few colors going while we're working. All right, the next one here is chromium, and I can see that there's a +2 charge here, so that tells me that I'm dealing with an ion. And not only am I dealing with an ion, I'm dealing with a monoatomic ion because it's all by itself. There's nothing else there. So we can then look at our list of rules, and I see rule number 2. The oxidation number is the same as the charge of the ion. Let me erase that and actually get the whole thing. Charge of the ion. So since this has a charge of +2, the oxidation number is going to be +2. Some things to start noting now that we have charges is that the charge goes before the number when we're talking about oxidation numbers, and when we're talking about charges, you'll see that the positive sign goes after. So after number for ion charge. do keep that in mind. That's part of the chemistry language that we're looking for. All right, now let's start combining some rules together and seeing some examples. I'll put this probably in the green color now. So again, I want to figure out chromium, but chromium is now, in what I can see, is a polyatomic ion. So with that polyatomic ion, I realize that there's chromium and there's oxygen. So I need to start combining multiple rules together. Now, I don't know chromium because chromium isn't involved in anywhere on that list as its own kind of set of rules. These chromiums I figured out because they were following the element and the monatomic ion rule. So I need to use oxidation math to figure out chromium. Next here I have is oxygen. So oxygen, I actually do have a rule for, and that's rule number 5. And it says the oxidation number of oxygen in compounds is usually -2, with the exception of if it's in a peroxide or if it's with a fluorine. When I look at this guy down here, it's not hydrogen peroxide. It is not with fluorine, so it's going to follow the oxidation number of -2, following that rule number 5. So oxygens ON is equal to -2. Now I need to start doing some oxidation math. If you guys remember, do I have any more colors? Oh, because I'm going to use gray. Polyatomic ions, the total charge of that polyatomic, or sorry, the charge of it is going to equal the sum of the various oxidation numbers, and that's using the 4th rule right here. The sum of all oxidation numbers. So let me show you what I mean by that. We will set this up as an algebraic equation. So I have 1 chromium atom plus 4 oxygens, and together they're going to form the polyatomic CrO4-, which is, I can't remember off the top of my head. Anyway, now let's try to substitute our numbers that we know. So we don't know chromium. We can treat that basically as an X. I'm going to write that actually as X, so that way you can see the algebra. There's 4, and I'm multiplying it by -2 because that's the oxidation number of oxygen, and I'm setting that equal to -1 because the rule is polyatomics, we set it equal to the charge number. If I was dealing with a neutral compound, I would set it to 0. So I have X equals -8, or sorry, X plus -8 equals -1. So that's just the 4 times the 2. I want to get X by itself, so we are adding +8 to each side so that the 8's cancel out, and I get X equals to +7. So chromium's oxidation number is going, I should say, in this polyatomic, because it's going to change. And you can see what I mean. It is changing in these different examples, and depending on what reactant and product I have, that then tells me if it's going up or down. So that's my chromium in that case. So you can see there's 0, there's +2, there's 7, depending on what's on the reactant side, what's on the product side. That number is going to increase or decrease, and then that helps me tell if it's oxidation or reduction. All right, let's do one more with the polyatomics. We can't use that same number over again, so we can't assume that the chromium is going to be 7 in the polyatomic. It really depends on what the polyatomic is. So we'll do the same setup as we did before. Chromium is my unknown. Oxygen I do know is -2, same conditions. It's a polyatomic. Let's set up then as our equation. So I have 2 chromiums plus 7 oxygens is equal to my dichromate. Then let's start substituting numbers in. So this is going to be 2x plus 7 times 2 equals -2. And then let's do the math. So 2x, forgot the negative sign, plus -14 equals -2. Now I need to get rid of the 14s. So I add 14 to each side. The 14s cancel. This becomes positive 12 equals 2x, and then I need to divide by 2. So you have to remember that in this formula there are 2 chromiums there, and I only need the oxidation number for 1. So as a note to remember, whenever referring, whenever we're referring to oxidation numbers, you should be writing about 1 atom. Reference to 1 atom. So divide by 2 on both sides, so x equals positive 6. So chromium's oxidation number in dichromate, which is that molecule, is equal to positive 6. So we can see in these various examples how different these numbers are. This one was positive 6. This one was positive 7. That one is positive 2. That one is 0. So those oxidation numbers can change, and that changing of oxidation numbers can help me figure out if it's an oxidation reaction or a reduction reaction. So like I said, if the oxidation numbers increase, you have lost electrons. That is an oxidation reaction, making the reactant a reductant. If those oxidation numbers decrease, then that makes it a reduction reaction. You have gained electrons, Leo says grr, and then that would make the reactant a reductant. So do lots of practice with this because it is very easy to kind of get this terminology mixed around. Anyway, oops, too fast. All right, Kapai, congratulations on finishing the second lesson for this week. So you should be able to process the rules to help you determine oxidation number. For your recommended follow-up, do the tasks that are listed in lesson number 2. You don't need to do all of them. Just do what is right to your level and how much you need to do to understand what's going on. Don't forget to show that evidence in that week 6 Google Docs. Either insert images or type up your answers there. Once you feel confident, do the CPR quiz number 1. That will help you practice redox vocabulary, simple equations, and oxidation numbers. There are lessons posted to this lesson number 2, so you can check your work. And like I said, all these Google Docs are assigned under Google Classroom for week number 6. So that is everything. And hopefully all of that makes sense to you. If not, contact your teacher.